Welcome back. So today we're going to do invert binary tree. Still in week 1. Lots of questions. Lots of questions to do. Invert binary tree. So binary trees are the basis of binary search trees. Search trees have special conditions where the left subtree must be larger than the right subtree. All the values in the left larger than all the values in the right. And there are some special trees that we can create to balance them. This one is only a binary tree, so in the binary tree, the only condition really is that there's going to be a left or a right, so at maximum there's two children only. So invert binary tree. Given the root of a binary tree, invert the tree and return its root. Okay, so returning its root gives us a clue that we either need to save the root, or that when we rebuild this tree, we're going to be returning this completely rebuilt structure. Okay, so here's an example. There's a 4, a 2, a 7, 1, 3, 6, 9. Okay, and now the 4, I see, now the 4's dot left is the 7, the 4's dot right is the 2, and then what happens on the 7? So the 7's dot left is now the 9, and the 7's dot right is now 2. Okay, so I guess if you have a function and you're given a node, you basically want to swap the 2 pointers, right? You have a left pointer, so put left and right. So whatever was on the left, I'm just going to pretend this is a reference to 1, and this is a reference to 2, right? The numbers don't make a difference. I'm just saying that these are 2 different references. We want to swap them. So if you have a tree here, and this is left, right, and this is the node, you basically want to take this left, and just to make it clear, I'm going to make that a different color. So the left is this blue, right? And the right is this green. You want to take this left one and move it over. Take this green one and move that over here. And just like you're doing it in the diagram, you could see that you kind of need like basically a temporary space in memory to store it, because as you're moving it, you want to move them safely. What I'm saying is that if we started with the default behavior, so let's say these are not moved yet. If I just moved, so we're reassigning left and right. If I reassigned my left with this right, I'd basically overwrite that left. And now my right is, actually, it's actually not the correct example. The example would be if I reassigned left. So let's say I'm given a node, and I'm saying that the node dot left equals the node dot right. Then I'm essentially moving my pointer, this left pointer, to this right side, right? So it's like I'm taking both pointers and I'm pointing to this node. And now this node has nothing pointing to it, so this will actually be garbage collected in a garbage collected language. It's just going to disappear. I'm not going to be able to reference it. So what I want to do, instead of moving that left pointer over, is I want to probably store this in some type of address where I can save it for later, move this over. So let's just actually write this in code. So in this swap, right, if swap is my intention, I want to, let's store node.left is here, and then node.left, which is actually the reference pointer, right? So it's not the actual address in memory. This is now going to be the pointer. I want the node.left to equal node.right, right? And so at this stage, it's going to be that. And then when node.left is equal to node.right, then it will be as if I'm moving this pointer to here, to right. And then I could do node.write equals this temporary thing, which is this one. So node.write now equals this temp, right? Imagine this temp is over here. So the node.write is equal to this temp. So I've switched the two positions, right, based on this swap. And I need the temp and kind of figure that out by drawing this diagram. Okay, so just going to go ahead and delete that, delete this. So given a node, if I do this for a single node, then this swap will work for that single node. What happens now is that I want to I want this to happen recursively for all other nodes. So, I basically want to call this function. I'm going to make this gold here so you can see it. I'm going to call this function at the root, and then I'm going to call this function on this node, and then I'm going to call it here, 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 everywhere, right? So everywhere where I'm able to call this function, I'm going to call it. So I'm going to go ahead and call this function. I'm going to use the word recur here, and it's going to recur on node.left, and also recur on node.right. Now node.left and node.right might be, it might be none. So you can go ahead and, if node is none, just, return. So that's going to be so this style is going to be changing these pointers in memory. It won't be building the tree, building a new tree like we've seen in different problems. So in different problems, if we do this recursively, each node, when a function is called on it, is returning something else, right? It's returning itself, it's returning some value, and then when you're getting the recursive version of them, you get to make a choice, right? It's probably more clear if I write that code, but I'm going to refrain from doing that for this problem because we don't really need that. So here's kind of all we need. So you can imagine, let's make that function. So let's make this smaller so we can see it. So the function, I'm just going to call it go. It's going to take some node, and what it's going to do is, if the node is none, it's just going to return. It's going to do nothing. And then we're going to build this swap, right? So this swap is going to do a swap, and then we're going to do recursive calls on both sides, right? The swap is going to do a save. So temp equals node.left. The node.left, the pointer is going to now point to a new node, which is going to be node.right. And then node.right, that pointer is going to point to what we saved here in our little our little spot for the temp, and that's going to be an inversion, right? And the recur is just calling recur, and here it's going to be the node, going to be node.left and node.right. So definitely have to call this, and then we want to return the root. So let's think about cases where this works and where it doesn't work. What about the case where the root is empty, right? So example 3 here, the root's empty. So if the node is none, return none. So it's just going to return root. So nothing's going to happen. It's going to return root, and it's just going to return none. Perfect. What about example 1? If you pass in a 4, the node is going to, that's going to be the root of, the root's going to be 4. It's going to save this, so it's going to save that 2. It's going to assign this left, right? So let's just draw it up here. This would be a 4. This would be its left pointer, and this would be its right pointer. And this would be a 2, and this would be a 7. And let's just draw this temp right here. So if we just, think through it, the temp is going to save this node.left, and then node.left, the actual node.left, is going to point to this right array here, and then node.right is going to point to this temp. So it's been successfully switched, and then it's going to call recur, or it's going to call go on node.left, right? And node.left now is going to be the 7. So it's going to call it on the 7. What does the 7 have? The 7 has 6, and it has a 9, and this is its L, and this is its R. So it's going to, save this 6, essentially move the 9, and essentially move the 6 here, right? And it's just going to keep going. And that's seemingly exactly what we have to do. All right, so let's submit this, and let's just understand that, what's happening here is that this L and this R belong to this node, right? So this node, if you look at the class, the tree node has a value, it has a left, and it has a right. And the left and the right are pointing to, potentially this node or this node, and we can easily reassign it, right? We can make node.left a new node. It could be an existing node. It can be anything we want. The idea is that we can reassign these. And an important thing is that we have to have this temp, because if we try to just reassign it, maybe in Python it works, but if we try to do node.left equals node.right, that node.left is going to be immediately garbage collected. But maybe we can do something like this, where node.right comma node.left equals node.right. I've never tried this before, and maybe you'd have to make this a tuple actually. I don't know if this is valid Python, but you'd imagine a language that had destructuring of a list, it could do something like this, right? Okay, it looks like it's not working for some cases. And I wonder if it's because of the syntax or because of something else. Doesn't matter. You don't want me to sit here and make a Python syntax, but the idea very much the same, right? Like we want some type of temp. We don't want it to be destroyed, and then we want it to appropriately make that switch. All right. Thanks a lot.